All right, pick it back up with another part. And since I'm home now to finish this lesson up, I will pick up with my iPad. We left off with the product of complex numbers. And as I told you maybe in the previous video, it's the same thing as saying 2 plus 5i, and you want to multiply that by 3 minus 6i. But these are complex numbers in rectangular, and we aren't presented with them in rectangular. We're presented with them in trigonometric form. Now, you could always convert your number if you were given a 2 cis of 13 degrees times 5 cis of 60 degrees. You could convert that into rectangular like we did in the other page, but you don't have to, because we have this formula that on the other video I showed you, that we take both radii. It's a radius. Actually it's a length, but it is r when you talk about the unit circle and you talk about the length from the origin. It's a length. You have two r's that we're going to multiply together, and we have two angles that could be different. They could be the same, and we add those together to create what the shortcut would be: the product of r's times cis. Which, reminder, well, there it is right here. What does cis mean? It means you have two different. So he didn't. This is not the. This is what's happening with two in shortcut form, but it could have started out like this. You got the long form, because you got the cosine of an angle plus the I sine of the angles. So we're going to practice using the product theorem. It's really, it's really simple formula, so you should have it memorized. It's making sure that we add up everything correctly. So we want to find the product of 3 cis of 45. I'm going to call that 3 cis of 45 degrees. And I'm going to call this 2 cis of apparently 135 degrees. So when I do my product of that, everybody understands this could be 6 something. 6 what? 6 cis of 45. 6 of 45 degrees plus 135 degrees. Hopefully they come out to be easy numbers to work with. I think earlier I was doing it and I didn't see the 100. And I thought, oh no, what am I going to do with a 70, so 40, 50, 60, 70, 45, 55, yeah, 45, 55, 75, 80 degrees. I don't know how to do that in my head. That'd be a calculator, but I added wrong. It's 6 cis of 180, which is better than 80, okay? Because I can do that in my head. So that means 6, the long form, just so that we know what's happening. 6 outside of cosine of 180 degrees plus the I sine of 180 degrees. So whenever we do products or the quotient coming up, is you always need to calculate, well, what is cosine of my sum of the angles? 180 degrees. I need to know that. And I need, what's the sine of, that's why I was worried about only having an 80, because I don't know that in my head. But the 180, we know where that is. It lives over here. And that ordered pair is negative 1, 0. So we know that the first number is your cosine, the second number is your sine. So we know that the cosine of 180 is a negative 1, because that's the x value. And the sine of 180 is the 0. It's the y value. So my final answer is looking like 6 out front of a -1 plus the 0, that's just plain -6. Now we could ask ourselves, what does that mean? It wouldn't hurt for us to look at it graphically and see what kind of complex number is a -6. Well, if you look at a plus bi, a has to be the real number part. That is a real number. So it's a -6 plus 0i. How does that look like in a graph? Just for fun. Well, if the x-axis is my real number, it's my a, and the y-axis is my bi, it's my imaginary part, it's clear to me that I'm going to go 6 to the left, 1, 2, 3, 4, 5, 6, and I'm not going to go up. So the vector looks like it goes out to here, starts at the origin, goes out to here, and boom, there it is. So that's the graph of that complex number. All real numbers are complex. We talked about that, a long time ago. Just because there's 0i doesn't mean it's not complex. All right, let's go. No, he jumps to the division. The division. Next formula. It's the quotient formula for dividing complex numbers. It shouldn't be any surprise to you that if I am dividing two complex numbers, and I could have just as well, as I said before, 2 plus 3i divided by 5 minus 6i would be a division of complex numbers. And we did that a long time ago, but we kept it in rectangular. When I say rectangular, it's because you can graph it on the XY plane. And so we'd have to multiply the top and bottom by the conjugate of the bottom. Remember that? But what if you didn't have it given? What if you were given in your trigonometric form or your polar form? Here's your r of cis. Here's another r of a different cis of a different angle, because you see the subscripts 1 and 1 and 2 and 2. But the formula is very easy. You're going to take the two r's, and that becomes division instead of multiplying. And instead of adding that, these two angles are the same, remember? So instead of taking these two angles and adding them, you will divide them, top minus the bottom, okay? So it's a very simple formula. And there is your answer in your long form. I like to abbreviate it and just say you divide, and it's cis, and you subtract. So it's not hard at all. And so when I'm looking at this problem, he's already written it in cis form. So my hat's off to the author, because that's what I like to see. In cis form, then I know that my quotient will be 10 divided by 5. I hope it's still 2. I think I did it earlier today and I put a 5. And then cis, may as well keep it in cis form. -60 minus 150, and I got to be careful because I lost the negative the other time I was doing it too. That's 2 cis of a -210, which is very important to realize that, because if you do it wrong, you'll be off a little bit. 210, I like that number because it's a multiple of 30 degrees. And since it's a -210, I just got to go backwards and say I need 7 of the 30 degrees. Well, if I go backwards, here's 30, -30. Here's a -60. Here's a -90. Here's a -90. 90 and 30 is 120. Here's a -150. Here's a -180, which counts for 6 of the 30s that I need. One more 30 right here. One more 30. There's my right triangle. And if that's 30, that's going to be a 1, that's going to be a 2, and that's going to be the square root of 3. However, remember we're in quadrant 3, And quadrant 3 is important to talk about because we know when I talk about that 30-degree angle, and it's all about that triangle, it's all about that triangle of the 30 degrees, that's for sure. 1, 2, square root of 3. And when I say, well, what is the sine of that 30 degrees? Well, it is true, it's 1/2. And the cosine of that same 30 degrees is the square root of 3 over 2. But look up here. You notice that's a negative square root of 3. Because when you're in quadrant, well, I'm not in quadrant 3 down here. I'm quadrant 2 up here. In quadrant 2, your cosine is still positive. So that's okay. But my sine is oh wait, my sine is also positive. Yeah, I thought one of the answers was negative. I guess they're both positive. Oh no, the cosine is negative. That's right. Cosine's over here. I knew one was negative. Okay. But the sine is positive because it's in quadrant 2, and your y values are positive up here. And your y values are negative here. But the x's are negative over here, and the x's are positive over here. So, okay, I'm good. I was talking to myself. So the final answer looks like 2 times the cosine of that negative 210 degrees, which we just did over here, plus the I times the sine of negative 210 degrees. So these are the answers I'm going to be using because I wasn't really doing 30. That's my reference. I was really doing the negative 210 because I was in this quadrant here. 210 negative. So 2 times the cosine gave me the negative answer, negative square root of 3 over 2, plus the I, and the sine of a positive half. If you wanted to, you could look at it as 2 times negative square root of 3 over 2 plus I over 2. And then I don't know why I did that step, because when I distribute my 2 in here, I end up getting a negative square root of 3 plus an I. That would be my, and that's a 1I. It's just invisible 1. That would be my division problem for. It's not hard at all. You just got to keep track of, am I going negative angles, am I positive angles, and reference angles, and it's not too bad. Oh wait, that's it. Demois Theorem is going to be fun, and I won't get to do that till Tuesday. But Demois Theorem is doing problems like this. What if you were wanting a complex number like 2 plus I, and you want to raise that to the 12th power? Wouldn't that be fun? 2 plus I times 2 plus I times 2 plus I times 2 plus I times